Welcome. We have the pleasure to receive David Elbaz from CEA, Commissariat d'Ingénierie Atomique, where he's Director of Research at Saclay. He's an expert in the study on the origins of star galaxies and their black holes. Main contributions is in the relations of star formation rate and masses of the galaxies, the identification of distant galaxies, and the main tool of the studies is infrared, where he has mostly worked using the data of Herschel, Spitzer, and Mauna Kea, and now JWST. He is so we said Director of Research at CEA. He's managing editor of the Journal of Astronomy and Astrophysics, and he has gotten prizes from the French Academy of Science, the American Astronomical Society, etc. And you may have seen him on TV and YouTube or different activities of science dissemination, where he's very he explains very well to large publics. He has written books, and he presents science in different media. So the work on JWST, we had the first presentation on the mission by Pierre-Olivier Lagage, who is in charge of the MIRI instrument. And now we said that it would be interesting, of course, to have a second, more cosmology oriented talk by David.
Thank you, Satiris. Hi, everybody, and I hope everybody can hear me from Zoom. So I decided to start this presentation with a beautiful image so that I don't forget to show you a beautiful image. But the topic of today's talk is not beautiful images, because you have seen them on the internet, on the news, everywhere. So I thought that it would be more interesting if I came here to speak about something new, something that you haven't read yet, some unexpected results that came out of the James Webb that we are still trying to figure out what's the reason for that. So that's going to be the main topic. It's not going to be exhaustive. It's going to cover several topics, but mostly on the distant universe. I won't speak about exoplanets. And the best experts in the world have been looking at those images, so you can imagine that those results have been studied in at deep levels, and you can expect beautiful theories to come out of those observations. So after 10 months after the first data release, which came out a few days, 2 days after the speech of Joe Biden on Monday, 11th of July, 2022, many results came out of James Webb, and I am mostly interested in what is unexpected, the surprises, because that's where, in some sense, we might gain insight on physics. So first, let us remember what were the highlights of Hubble. Hubble was launched 30 years more or less before James Webb, and it was able to discover already very distant galaxies, including this galaxy with the poetic name of GNZ 11, discovered in the good north field with a redshift of 11, which is about 400 million years after the Big Bang. And after this discovery, you might think, well, why do we need to spend $10 billion to have an extra satellite to look in the early universe, since already we have these galaxies from Hubble. Hubble revealed the shape of galaxies. Why do we need James Webb, since we already know the shape of distant galaxies? Demonstrated that galactic black holes, supermassive black holes, are ubiquitous. So we knew there were black holes in galaxies, not only in quasars, but with Hubble, we understood that the question was not whether there are black holes in galaxies, but whether we are able to find a galaxy without a black hole in the center. So that's a complete change of perspective. And of course, the question is, how and when did the supermassive black holes form and ended up in the center of galaxies. It was able to refine the measure of the age and expansion rate of the universe and to confirm, in some sense, although there are some tensions with the Hubble constant, but the standard paradigm of lambda CDM, at least it's presented like that. And is James Webb going to question that or not? And to detect what water vapor in the atmosphere of giant exoplanets. So when you see all those beautiful results from Hubble, you can think, now, what can you see with James Webb that we haven't seen before? Are we just going to see beautiful pictures, beautiful colors, and try to hide the fact that the science is not really different? Or are we really seeing something different in terms of science and not only images? Now, the promise of the dawn of the universe that I'm talking about is the fact that there was a time after recombination during which there was no star formation yet, which is called the Dark Ages, that has lasted for a certain amount of time, and after which came the first stars called the population 3 stars and the first galaxies, and also the first black holes, and that produced the first radiation, light in the universe. And the question is, when did that happen? And did the first stars come in a large enough number to explain the reionization of the universe? That means that after recombination, the formation of atoms were broken in the space between galaxies. And do we understand that, or do we need to invoke new phenomenon, new energies, something else? Now, between the moment when James Webb was conceived and the launch, turns out that Planck showed that reionization ended around redshift 6, and the stars we already knew to form in galaxies at redshifts of around 7, 8, 9 seem to be already very efficient to explain the reionization. So it's true that this key question of reionization is not such an issue at the time of the launch of James Webb. So people could say that in some sense, it comes a bit too late. But we're going to see that, in fact, there are other questions and that those questions were not necessarily expected. So population 3 stars, just say a few words about them. They are supposed to be the first stars formed out of metallicities, which are very low. And as soon as you are below 10 to the minus 4 or 5, the opacity is less efficient, the cooling is less efficient. So therefore, you don't fragment into small stars and you have big things. So you can form stars of several hundred solar masses. And the most massive of them will end up forming a black hole without even exploding. That's what theory says. Of course, it has not been observed. And they have been expected to be the seeds of supermassive black holes in the center of galaxies. The signature of those stars is, for example, the line of helium, ionized helium, around 1,640 angstrom, which is supposed to be about a third of the H-alpha line of hydrogen. And you have to see it without seeing oxygen and carbon to know that you are seeing stars formed out of primordial matter. So that's a bit one of the objectives, not to detect individual population 3 stars free floating in the universe, but potentially galaxies, primordial galaxies made primarily out of population 3 stars. And then, of course, trying to search for the first black holes. When did they form, and how do we understand what are the seeds of supermassive black holes by this observation? Before going into the science, I just wanted to tell you, I don't know if all of you are aware of the reason why the satellite was called James Webb, because James Webb hasn't invented anything or discovered anything. He was just the NASA administrator at the time when John Kennedy decided to do a breakthrough in science, which was to go on the moon before the fucking Russians. And that was the main scientific objective. And there is a very nice discussion between the two, which has been registered. And you can listen to that on the web if you go to this link. And I have it here, but I'm not sure you will hear it well, but I've put some of the text here. And it's really interesting because Kennedy tells Webb, you know, I want to go on the moon before the Russians. And Webb says, okay, I understand, sir, but if you want to do that, because the Russians, they have a bigger rocket, and also they are very much advanced, and they have made much more progress in space than us. Therefore, we need to to get the best researchers. And if I just go back to the institute and tell them that we just want to be faster than the Russians, we won't get the best guys. So we have to tell them something like they're going to do science, they're going to understand space or whatever, or this kind of thing. And then Kennedy says, okay, I understand these things, understanding what's the origin of cancer, solving many big issues for humanity is interesting, but that's not my goal. My goal is to go on the moon before the Russians. And then it turns like that. And then the third person says, sir, I think Mr. Webb wants to say that I understand what he says, but I'm saying that I want to go on the moon before. And James Webb tells him, you know, I have the feeling that, you know, the story on Cuba, alone wouldn't have been enough. I mean, if we hadn't flown John Glenn in space and showed that we had the capability, that wouldn't have turned the same way with the Russians. I know, that's exactly why I want to go on the moon. So clearly there is nothing connected to science there. But at the end of the discussion, Webb insists, and then Kennedy says, okay, write that on a piece of paper and I'll see. And then he leaves, and then there is a third person who tells Webb, but you won't tell him that you are already using part of the money for science? Nah, he doesn't need to know, it's okay. So, so the whole thing we're going to talk about are these things that he doesn't need to know, this little detail money, that the overheads and of the Apollo program and stuff, and the whole science came out of that. And the reason why Joe Biden is presenting also these results is because it's the continuity. James Webb is the continuity of the quest of putting the foot on the moon, and then you put the foot on the most distant galaxy. And in some sense, you show that you are the best. So we are not only understanding we think we understand the deep universe, etc. They think that we are demonstrating that a certain civilization is better than another. But okay, so that's important to know also, that it's not only pure science, but it's historically, we are part of this history. The first concept of James Webb came out of a French engineer, Pierre Bailly. I don't know if you know him, in the 80s, was working as engineer-in-chief at the CFHT, and then with Hubble, and Giacconi was the head of NASA at the time, asked Pierre Bailly, Peter Stockman, and Garth Illingworth to think beyond Hubble before even Hubble was even launched. And the idea is that everyone knew that there was a limit to what Hubble could see. Then came the idea of the next generation space telescope, and you can see this drawing, which dates 1996, and which is already looking a bit like the JWST that you have seen in space. So it's coming from very far away. A few last points on these technical aspects is that you can compare Hubble to James Webb, and of course Webb is bigger, but in fact in the same wavelength range you have to compare it to Spitzer, which was only 85 centimeters wide. So it's a gain of 50 in collective area and therefore sensitivity. And here is a simulation showing the gain in image quality that we did with a student where we simulated the universe that James Webb would see, and you can see that it's very different. A few technological breakthroughs. First, deployable mirror in space, and the largest. First telescope in space, first multi-object spectrograph in space, and first mask coronagraph in space. And the imager MIRIM of the instrument MIRI, observing in the mid-infrared, was built with a CA as a main contractor, so by France, and it is playing a key role in understanding, in particular, the atmosphere of exoplanets, but I won't speak about that, but also distant galaxies. Webb is real. We went on the moon. The Earth is not flat, and James Webb is in space, and you can see it with Gaia, and it's the little dot that you can see here. So we can, it's real. It's not deepfake. And the orbit diameter of Webb is 1 million kilometers, and it's 1.5 million kilometers away from here. So it's not on L2. it's nearly as far as L2 from L2 as we are from. It's really orbiting very far out of it. And the difference of temperature between the outside part and the inside part of these panels that protecting from the solar radiation Webb is between 85 degrees and minus 233 degrees. So you see that there is a huge difference here. So every week, the whole week of commands are sent in space, and then observations are done, and they can be corrected every day. The orbit is about 6 months, so it's a huge orbit around 0.02 L2. And the observations I'm going to describe from which came those results and surprises come from both guaranteed time observations and open time observations, with this idea that follow up on the Hubble deep field, the big programs are released immediately to the public and everybody can study them. And in fact, what's happening is that people who are not part of the collaborations often try to publish the first papers. So that's nice because it's open for the community, but it's also a good reason to expect big mistakes. And of course, people have been debating about that. I'll say a few words about that. But let's not only focus on the mistakes, and let's try to keep also the interesting surprises. And of course, we can debate about the mistakes. There is no galaxy at redshift 16. There is no galaxy at redshift 17 until now, and various other mistakes like that. Interestingly, James Webb was launched the day of Christmas, and the Hubble Deep Field was observed the day of Christmas, plus or minus 5 days. So this is a very nice present. And in 10 hours or 12 hours, James Webb is going potentially further than Hubble. Actually, is it really true? So the first redshift that came out of this very deep image from the James Webb showed galaxies seen 700, 800 million years after the Big Bang, 1.2, 2.5 billion years after the Big Bang. So that's very early on in the history of the universe. But how does it compare to what Hubble had seen before? The most distant galaxy with the Hubble was seen at a redshift of 11. So it's 415 million years after the Big Bang, which is earlier than all of those galaxies I'm talking about here. Now, James Webb observed that galaxy, made a spectrum with NIRSpec, and found that the actual redshift of this galaxy is 10.6, not 11. So it's not so wrong. And it's not Big Bang plus 415, but 436 million years. So it is confirmed to be an exceptional object and very interesting with a weird shape. And I'll go back to the shape of those galaxies very soon. After that came out a publication by a guaranteed time team. The collaboration is called JWST. And now the record holder from James Webb is a galaxy at a redshift of 13.2, 322 million years after the Big Bang. Now, I can hear what you're thinking because I can hear people thinking, and I know what you're thinking. You're thinking, okay, between 450 million years and 322 million years, there is not $10 billion. It is not what you would pay $10 billion for. I mean, and how does it change my understanding of whatever? Okay, I agree with you, with your thoughts. Now, let me reply to your thought. I will try to reply to your thought. First, let me go in your direction by telling you that not only it's only a few, like 100 million years, but also the helium-2 line is absent from the spectrum. So we cannot even say that this is a population 3 galaxy made out of population 3 stars with the high excitation of the helium that is what you would expect. So we don't know that. What we can say is that thanks to the quality of the spectrum, we can measure an approximate age of 70 million years for this galaxy, which would mean that it was born 250 million years after the Big Bang. So there should be galaxies at redshift 16 because this galaxy was not born at redshift 13. So there is hope to find galaxies further away, maybe not much further away. So the first galaxies may have been born about 250 million years after the Big Bang. We don't know yet if they are population 3 galaxies. And let's go to the surprises. First one, the galaxies we've seen are ultra compact. They measure the ones that have been seen by the guaranteed time people between 50 and 165 parsecs. It's not much bigger than a globular cluster, which is not a galaxy, which is a tiny little thing you can see free floating in galaxies. But that's the whole galaxy. How do you make a thing like that? I mean, that is a surprise because no one knows how to make that. Now, just a little thing you all know, but I just want to recall that when you see a thing that is small in the image, it's because it's small. It may look obvious, but it's not, because if I see something far away from me, it looks small, but it's not small, it's far. Here, the expansion of the universe counterbalances nearly exactly the fact that things are smaller because they are far. So as a result, the apparent size of an object, well, it has a curve, but is more or less such that 1 arc second is about 8 kiloparsec, about 25,000 light years at nearly any epoch. And then you can vary a little bit. So when you see things small, it's because they are small, and they are really, really, really small. We have seen these ones are very tiny, the ones of jades, and they are flow mass, but the other ones on the left that we observe in the program SEERS are a bit bigger, 500 parsec. So it's not anymore the size of a globular cluster, but still, it's still very, very, very small. So that's a surprise. Surprise number 2. Let me quote one sentence of Pascal Husch, who is the discoverer of GNZ11. A few weeks ago, we were discussing, and he said, well, we have seen in a few days more than what we expected in a year. So I just told him that, okay, that means that what you expect is wrong. It doesn't mean that it's something unexpected or like changing our life, because it all depends on what do you expect. So that sentence doesn't mean a lot, but it just means that we, based on observations and extrapolation of observations, or based on models, more or less 100 times more galaxies have been detected, or they are brighter. Therefore, the more numerous low luminosity galaxies turn out to be more luminous, and therefore you have more of them, or maybe even more massive. So let me show you a few reasons why people think that through a few papers, and what are the consequences of this surprise. So that in that representation, it's about a factor 100 more galaxies. This is the number of galaxies as a function of magnitude in the UV. So we are in the ultraviolet, even though we are looking with James Webb in the infrared at redshift 12, you are in the UV. So you are like Hubble, but further. And so you have more galaxies than expected, and no model preceding James Webb has predicted that. So is that really important, or is it just a minor correction? This is the key question. Another way to look at that is the luminosity function at redshift 9. Instead of having a drop of galaxies that you usually expect in what we call the Sechster function, at high masses, you don't see any drop. So that means you have much more galaxies, more luminous at those redshifts. On the right, what you can see is various expectations from models of the number of galaxies at redshift 12 you would have expected with those magnitudes. And you would have expected at most 1, and you get 4. So, and in most models, you would have expected 0.1. So clearly, something's going wrong. I mean, compared to what was expected. Now, of course, there is always someone that wants to say more. And so Ivo Labbé was that one, and he published a paper in Nature. So for those who don't know, a paper in Nature is a paper that has to be wrong, but you have to wait usually a few weeks. This one was wrong before acceptance, but it was still accepted with a new version. So there is 2 versions, the one before acceptance, the one accepted, and I will be more interested by the third one, which is another version that he presented a few weeks ago. And so just to be more confused about the thing, but I will try to clarify. I close the parenthesis, and it's not because I'm jealous. Huh? I am also jealous because, you know, we all want to publish in Nature, of course, but sometimes you're not wrong enough, so you're not accepted. So, so the paper of Ivo Labbé thought, I mean, okay, they are not seen in the res frame 1 micron. Therefore, you cannot really measure their masses, but let's say you can guess them more or less. And if you do so, and at redshift 7, at redshift 8, at redshift 9, bon, you can more or less have relatively good masses, unless something I will say after. And if the masses are correct, you can see here the dashed lines are what you were expecting, and the colored zones are what you observe, and you see they are not overlapping. So there is more galaxies, or they are more massive than expected. Now, what does it mean? To know what it means, you have to read the news. And in all languages that you can imagine, the news is a shock because a few galaxies are destroying everything we knew about the universe. And that's in all languages, in Korean, in Russian, in whatever. So he got the first page of all the news. And he's still now, they are still having that. The reason is that what Boylan Colchin published just after the paper of Ivo Labbé is that if you take all the baryons that are in the dark matter halo, you convert them in stars, all of them, you barely make those galaxies. And we know that in a dark matter halo, the amount of baryons converted into stars is about 10, 15% or something like that, if you want a bit more, but not 100%. So, and even with 100%, it's marginally possible. So either you change your cosmology or you say that dark matter makes stars or whatever, I mean, the authors here were considering the possibility to rule out lambda CDM based on those galaxies. And it's probably true that if those galaxies are at those redshifts and have those masses, it is a problem for lambda CDM. And that's also seen by Menchi et al. On the other side of the cosmological paradigm, which is the dark energy. You can rule out lambda CDM, where you can rule out the lambda, the dark energy, as a cosmological constant at better than 90% level, assuming again you convert 100% of the baryons into stars. Now, if you convert only a fraction, you can rule out lambda by 99%. So clearly, it's a surprise first. And it's opening some questions on what can be happening there. One possibility, which is the one we favored in a paper led by Steve Finkelstein, is that when you form stars, you have a few massive stars that make a lot of light and many low mass stars which make not a lot of light. 1 solar mass star produces 4,000 times the luminosity of the sun. So if you don't know what's the mass of a star, and if you look at the light only, you might be wrong by factors of hundreds easily when you derive the mass. The mass is done by the low mass stars. So if you have a few more massive stars than what you would expect and what you have expected to measure the stellar mass of your galaxy, then you can be completely wrong. So if the galaxies have a bit more stars, massive stars, then the masses are much lower because they produce more efficiently light, and therefore you don't have any problem with lambda CDM. There is also an expected amount of dust in those models, little, but still. And if you take out that dust, you can produce more light because you have less absorption. Last, you can have galactic black holes in the center that produce light, and there you cannot use that light to determine the stellar mass of the galaxy because that light is due to matter infalling onto the black hole. So the question is, are we seeing black holes at more abundantly than expected? Are we missing something? Is what we think, is it that when we think that galaxies are powered by young stars, they're actually powered by black holes? Let's go back to this most distant galaxy seen by Hubble, GNZ 11. And let's look at its spectrum in detail. And what we see is lines which are high excitation lines, which are typical of AGNs. So in fact, this galaxy is not a normal galaxy, it's a little quasar. So we can see that at redshift of 10.6, you have already a supermassive black hole in place, while the record before was around redshift 7. This is not yet published, but it will come out in some days. Now, what is published is another record, which is a galaxy with the spectral signature of black hole. So high excitation connected to matter accreted by a black hole at redshift 8.7. And the black hole mass is about 10 million solar masses. So that and other observations is telling us that the standard paradigm that we had before, which to form supermassive black holes, seems to be ruled out by most specialists now. So that's a surprise. What was the standard paradigm? Standard paradigm was that you would form a seed supermassive black hole by a population 3 star and let it grow with time. Now, if you do that, you cannot produce the black holes we see that early in the universe. So you have to assume super Eddington conversion of accretion into light, but really extreme. So the most probable is that you form supermassive black holes directly at masses of a few tens or 100,000 times the mass of the sun in the galaxies. Now, since that was found, when I discussed with my colleagues who were making supermassive black holes with population 3 stars, they admitted that there was a caveat in their model. If you make a seed black hole with a 500 or 1,000 solar mass star that becomes a black hole, a tiny black hole, why would it end up in the center of the galaxy? In fact, that was a big problem because there is no reason it will fall in the very center of the galaxy. But the supermassive black holes we see, they are in the very center of the galaxies. So now they say, okay, we didn't mention that before, but now that we know that it might not be the right model, maybe we can tell you that our model, in fact, was a bit problematic because of that. So it was below the carpet. So James Webb is taking out the carpet and telling you that there were issues before. And one of them is that black holes must form earlier, faster than expected. So not only stars. Surprise number 4, spiral galaxies like the Milky Way were already in place, even though smaller, a few 100 million years after the Big Bang. That wasn't expected, especially after what Hubble showed, which were very irregular galaxies. Now, again, Hubble seeing a distant galaxy, looking in the UV, can only see the massive stars. Therefore, it cannot see the shape of the galaxies and their mass, which is due to the low mass stars. In other words, it cannot distinguish a squirrel from an elephant. With James Webb, we can distinguish a squirrel from an elephant. Now, Hubble was seeing very irregular galaxies, but are there squirrel or elephants? This is an example here. On the left, you have the squirrel seen by Hubble, which is a very compact, irregular galaxy with a clump in the middle and maybe some other colleagues on the side. Seen by the James Webb, it's a very nice, relaxed spiral galaxy rotating with a shape that has nothing to do with the one of Hubble. And that is coming from the combination of the size of the mirror that gives you ability to see diffuse emission, as well as the sensitivity and the wavelength. In the end, we see spiral galaxies over the whole history of the universe, well-shaped with a lot of barred galaxies. And I will tell you why it's important. But it's already a surprise that spiral galaxies were informed early on. And one reason why we should be surprised is the following. If you think that galaxies are formed mainly by mergers, that should destroy disks. And yet you see disks in place very early on. So in some sense, James Webb resurrected the fork that Edwin Hubble lost with the Hubble Space Telescope. Just to show you again this image I showed in the beginning, what you see with MIRI in this image is very interesting because the color that you see here is due to polycyclic aromatic hydrocarbons, so complex molecules, which are radiating at the wavelength observed by MIRI, and are formed in the spiral arms of the spiral galaxy. And you can see holes produced by supernova explosions. And on the surrounding of those cavities, you see an excess of star formation and molecule formation, which is an illustration of the fact that star formation is induced by supernova explosions. So, that's a very nice illustration of complexity being formed in those spiral galaxies. The reason also why we're interested in the spiral galaxies is because we have found that star formation in galaxies takes place in a very smooth and regular way. We call it secular star formation. That means that if you take a galaxy at any given redshift, you know its star formation rate from its mass. And that means that it's not very much affected by the environment. And one way to understand that is that star formation is regulated by the rotation of the galaxy, which is preventing matter from inflowing into the center and keeping the star formation at a regular pace. So the rotation of galaxies is key to explain what we call secular star formation and what we call the main sequence of galaxies. Surprise number 5. Galaxies started to die or become passive earlier than expected. You see here a galaxy at redshift 4.7, which is seen 1.2 billion years after the Big Bang. And a zoom on its spectrum shows very deep absorption lines that are typical of stars that are moderately old. And if you had young stars formed, the continuum that those young stars would form would dilute those absorption lines and you wouldn't see them anymore. So that means there is no what we call OB stars here, but mostly AF and stars. And that means that there is no star formation in this galaxy since some time, typically a few hundred million years. Therefore, that galaxy is already dead in the very early universe. And the question is why? And that is really surprising because you don't, we know that we have many passive galaxies in the nearby universe, but to have a passive galaxy that early in the universe is an issue. And as you can see, the size of this galaxy is very tiny as well. I will mention a possible explanation for many of those surprises in the next slides. Surprise number 6. Globular clusters in galaxies are very common and old. An extreme case is the Sparkler galaxy at redshift 1.4. So it is seen 4.6 billion years after the Big Bang. And it is filled by globular clusters. And you can measure the age of the globular clusters inside the galaxy that are about 4 billion years old. Therefore, they were born a few hundred million years after the Big Bang. So those globular clusters were born at the time of the formation of the first galaxies and stars. So that means that the question is not anymore whether what came first are the stars or the galaxies, because it may be the black holes, or it may be even not the black holes, but the globular clusters. The first thing that's formed may be globular clusters. And we see them in many galaxies that we couldn't see before, and we can measure their age. We can even see intergalactic globular clusters showing the process of what we call galaxy harassment. Surprise number 7, the last one, but that I selected. We can measure metallicities from new diagnostics in the distant universe. So let me tell you what I'm talking about. In the spectra of galaxies, which are very distant, we see auroral lines, which we were seeing in the past, in the late universe, which are some specific excitation of the oxygen. And that means that the amount of lines that we see here is so large and so rich that we can build diagnostics to measure metallicities, so the amount of oxygen, iron, carbon in galaxies at the epoch of the early universe that you're observing. That's major because in the past you were relying on diagnostics done in the local universe. And why is it interesting? Because you're not going to see the most distant galaxy. What you want to do is to measure perfectly well the age of the stars of the galaxies that you see. And for that, you need to know how to measure metallicities. And that's now possible. So that means we're going to be able to deduce when the first galaxies formed, even though we won't see them necessarily in real, based on the metallicity measurements that we're going to calibrate based on distant galaxies. And that we did not expect at all. So, is the promise of dawn of the universe kept? We have seen distant galaxies, not yet population 3 stars. It's the beginning. But we have seen that there are many surprises that came out of the first month of observations. Galaxies are very compact. They are more numerous, brighter than expected. Supermassive black holes were found early on. Maybe they were the first source of light in the universe. Spiral galaxies were already in place very early on. Galaxies started to become passive earlier than expected. Globular clusters are very common and old. They may be the missing link. Maybe they were the first to form. And we've seen auroral lines that are allowing us to measure the ages and the metallicity of distant galaxies. So in other words, we just opened the book. Now, let me go back to a common potential origin of the first 6 surprises. I told you that if galaxies were formed by a series of mergers, they would destroy disks and you would not expect to see so well-relaxed galaxies. In fact, we already knew that because we knew that there was this secular star formation in galaxies. The common paradigm is the idea that you have cold streams of matter infalling onto galaxies. And those cold streams not only feed the galaxies, but they also feed the angular momentum that build the disk. And they have other impacts. One of them is that you expect to see lopsided galaxies if galaxies are formed and fed by these cold flows. And we see a lot of lopsided galaxies. What does it mean? It means that if you look at the center of the galaxy, the center of light, where you have the bulk of the light, is offset. And that can be produced when you form the spirals, when you produce the angular momentum by the injection of momentum from the infalling baryons onto the galaxy. You can build the angular momentum of galaxies by this inflowing matter, and we've seen that you see a lot of rotation very early on, and that can be due to this accretion. In a recent paper, it was shown that these cold accretion flows may explain how you form the first seed black holes, and you can form massive concentrations of matter just by the impact of those cold flows. Lastly, the cold flows are so efficient in bringing matter in the very center that in this paper published a few weeks ago by Deckel et al., it is suggested that you can produce what is called feedback-free starbursts. Therefore, that you form the stars before you have explosions of supernovae and all the effects that are preventing, regulating star formation, which could explain why you have an excess of galaxies and UV light from galaxies. And that could be due to the cold filamentary inflow. In other words, we may be seeing the signature of these cold flows by all those surprises that we see with the James Webb. Of course. Yeah, well, no, well, they are dark matter is an initiator of that, but you need the cooling of the matter to make the cold. So it's cold because it's baryons and because it's those cold flows could also explain how you make a passive galaxy early on. I belong to the Association of Defense of Supermassive Black Holes. Sorry, I should have said before. So I disagree with people who say that if there is a problem, it's black holes who caused it, and the black holes kill galaxies. The reason I say that is because we see black holes accreting in galaxies with various star formation rates, various masses of black holes, and it has no impact at all on the star formation rate of the galaxy. And they were formed early on. So therefore, I decided to be a member of this Association of Defense of Black Holes. And here in that paper, for example, which was published very recently, they say that you can produce a passive galaxy if it is close to more massive galaxies or bigger dark matter halo that will attract the cold matter and then deprive that galaxy from the infalling filament. So you just need to cut the filaments to make a galaxy passive. Here you have a paper that came out also very recently, which shows a potential detection of infalling cold flows with ALMA, provoking potentially the rotation of the galaxy with a C1 atomic line, which is a tracer of neutral gas. And finally, in that paper we published with Emmanuel Dadi, it's where we see some Lyman alpha emission possibly excited by the gravitational infall of matter. We see that this emission is proportional to the baryon accretion that you expect for the dark matter halo and could explain several properties of galaxies. and galaxy clusters that I don't have time to explain here. Also, we see a lot of bars which are signatures also of this called filamentary infall. So globally, many of those surprises may be the signature of this paradigm where you need to invoke the very efficient role of infall of matter from this cold filamentary flows to explain properties of galaxies. So I don't think we are yet in a situation where we can simply reject lambda CDM based on the observation of James Webb. So as I wrote, we just opened the book. It's just the beginning, and I will stop here. Thank you.
Thanks a lot. Questions for the speaker? Both in the room and Zoom. Yes. Prize number 6. Could you comment a bit on what are the evidence for older globular clusters than the embedding galaxy? That's two prize.
So for the globular clusters, what we see is that we can resolve them with the web. We can make spectra. We can look at the age of their stellar populations, and we see that these ages bring you back to a few hundred million years after the Big Bang. So, and that they are quite omnipresent in many of the galaxies that have been observed. Here I showed the Sparkler galaxy, which is an extreme case. But in many galaxies that are seen and resolved with James Webb, you see those globular clusters that are quite numerous. So the question that is here, what is surprising is first, they are quite abundant, and second, they seem to have formed very, very early on. So it's true that the globular clusters in the Milky Way are old. For example, you can see globular clusters 10 billion years old. But if you assume the Milky Way to be 12 billion years old, they may have been formed 1 billion, 2 billion years after the Big Bang. We don't have the proof that they were formed a few hundred million years after the Big Bang. And also, it may be an intermediate state to make intermediate mass black holes, because that's one of the options.
Complementary question.
Yeah.
The reduced size of these oldest galaxies makes them look like globular clusters.
Yes. Yes, they are a bit bigger, but yes.
Yeah, a bit bigger.
Yeah.
And so why not calling them globular clusters?
Well, it's a good question. The first people are, I mean, you have to accept the possibility that despite the power of James Webb, you may be missing low surface brightness emission and an underlying disk that you don't see. So that's possibly the tip of the iceberg that we're seeing. Okay. So that's the caveat that makes people think twice before going too far in conclusions.
The issue of this very compact galaxies is not really settled.
No, it's not completely settled, but still it is quite systematic. They are very compact, and it goes well in the direction of other observations. Like, for example, we see that you have very compact ellipticals at redshift 2, which already we didn't know how to explain. It's not that far, but and you have to form also the supermassive ion, so they have to bring matter in the very center. And some of those galaxies are 500 parsecs big, so not 65 or 100, so bigger. And those ones, they have a higher signal-to-noise ratio, so it's more difficult to hide the disk in those ones. So and I guess, I don't know if that's been done yet, but it's going to be done if it hasn't been done yet. You can stack them. You can stack many images, and if there is an underlying disk, you should see it. So, but I cannot say that we don't see it after stacking, because I'm not sure we have enough objects yet to do that, and I don't know if it has been done, but we should be able to do that soon.
Yes, Simone.
I want to ask you about these gas streams that go inside the galaxy, right? And you say that it resolves you can explain the surprise that we observe very early massive black holes. Now, how is that connected to the fact that the black holes formed very early and then we find them in the center of the galaxy? Can you make the connection?
Yes, I will repeat the question.
Yes.
The question is about this scenario where supermassive black holes are formed with the cold streams, and how can it explain the fact that they are formed very early and they go in the center of the galaxy. Here I was just quoting one paper that is suggesting that, so it's not like a new paradigm, it's just one paper saying that it would help. Now, the question is, when do the cold flows start? I mean, do the cold flows start early enough to make, let's say, 10 to the 8th solar mass black hole at redshift 10, for example? I guess it's too early, I guess, to answer that question. Now, whether they can put that at the center, that maybe yes, because there is a high probability that the cold flows will converge at the center of mass of the things, because it's driven by the gravitational potential. So the center should be fine. Whether it's early enough and massive enough, that I don't know. Yeah.
I have another question of the very massive galaxies. So these are very small numbers, and
Yes.
the area covered by JWST is very small.
Yes.
So do you think that, how do you exclude that this is not due to cosmic variance?
But you're right. It's one of the explanations. You're right. It could be just
The
by.
fact that if you observe in different directions, you will observe different number of.
Yeah, you're right. So that's one of the reasons why we have to wait a little bit further to see if we are not just looking. It's just that the way it was thought about by Boyle and Colloquium, for example, if the masses are correct, is such that you would need to observe 1,000 fields like that to get one. You could be falling on that one, because when you have only one field, it could be that one. It's just that statistically it's not comfortable. So that's why people are. So it's easier to say the masses are overestimated than to say that you fell on the 1 out of 1,000. So I would personally favor the fact that the masses are overestimated.
Yeah, maybe give us some more details about this helium-2 line that is sort of the sign of population-free stars. I mean, this is something that you should see in the future.
Yes.
The metallicity must have been produced somehow.
Yes. So in fact, we do see the helium-2 line in several spectra from the James Webb, but it is at a 10th of the Lyman alpha line and not a third, which is what you would expect if it was mostly hydrogen and helium, primordial gas. And you see also some oxygen and carbon and other atoms, the center of the atom. So therefore, we know that the gas has been enriched, so it cannot be the real first star. So it's not only that you want to see this line, but you want to see this line and not the other ones, and at a level which is high enough to be typical of population 3 stars. So we know that we won't be able to see an individual population 3 star alone. So what we hope is to see a kind of family of population 3 stars exciting their IS surrounding ISM and leaving this signature before this gas is enriched with oxygen and everything. I mean, it's not an obvious goal. Huh? It's not clear that we will get that.
And if you don't get that, you would need something that goes further in the infrared, or to see this kind of thing at larger redshift. Or do you have any thoughts about that?
The problem is that if you take those surveys with the James Webb, within hours, you know, even in the bigger fields observed by James Webb, within hours, you know which are the candidate distant galaxies, and you have a few. So you're covering a volume of the universe which is tiny. So it may be that you just don't have any accessible galaxy in that little tiny part of the sky that was formed there, because it's not like every part of the sky has its primordial galaxy. It's not just a question of going deeper, because further than, let's say, 200 million years after the Big Bang, there is just nothing. So it is not only that we are not sensitive enough, or okay, maybe you can go at lower masses and get more, but it's maybe if you had a 30-meter telescope and you would be able to see smaller galaxies, maybe you could see some and get more numerous objects to compensate the fact that the field is small. But the fact that the field is small is such that at the sensitivity limit of James Webb, you would need to observe square degrees to get one of those guys, maybe, and you won't observe square degrees. So we may just never get them. But yet we can still answer the question because we don't necessarily need to get them. We can measure the age of those we see, and that tells us something statistically on when the first stars formed. And what we want is a statistical constraint on the rapidity with which stars and galaxies form to be compared to our theoretical framework. That's what we want. We don't necessarily want to see the purely primordial galaxy as such.
So I'd like to follow up on what Simon was asking earlier. So what is how to understand what's the statistical basis on which you are making those statements? How many galaxies do you observe beyond redshift 10? And what are the numbers there? I have a follow-up question on the cold stream thing. So the question would be, you said that the lambda CDM issue may be resolved by those cold stream scenario. How are you going to address this issue with the James Webb data? Can you give an angle between those two things?
The two things being?
So the cold stream versus lambda CDM.
No, well, the cold streams are, sorry, I will repeat the question. So the question is, how many objects do we have above redshift 10 and what is the statistics there on which we base our discussion? And the second aspect of the question is the cold stream scenario that is used to save in some sense lambda CDM, how robust it is and how we can test it. So the cold stream scenario I presented here was the Deckel et al. Paper, which is what they call feedback-free starburst. You have to be aware that those models that were under-predicting the number of galaxies, they are based on some number of assumptions that you form stars with an initial mass function that is typical to the one, like the ones we see in observed galaxies today. So that's one thing you can change a little bit and it changes everything. And that once they start exploding, they inject some energy, there is turbulence, and you regulate star formation, and it doesn't go that fast. And therefore, you have less star formation. That's why you have less stars and less luminous objects there. It's based on those assumptions. Now, the starburst, the feedback-free starburst induced with the cold filamentary infall is such that you bring more efficiently than expected a lot of mass in a small region. That means that you form the stars before they even have the time to produce the feedback, and therefore you make most mass, more light per unit mass. So that is just telling us that you don't need to prove that scenario, because in fact it tells us that there are scenarios which are completely realistic that can explain the fact that we are underestimating the number of galaxies. Therefore, the time has not yet come to change the underlying framework of the cosmology on which the galaxies are located. So we are not here saying that we are converging on understanding how galaxies form their stars and their filaments and everything. We are converging on the idea that time has not come to reject the underlying framework of the cosmology. That's what I'm trying to say here. And it turns out that for each one of those questions, one scenario is connected to this cold filamentary infall. So it looks like a single thing can help and should be taken into account. And since it wasn't taken into account that carefully in those previous models, this is one of the simplest assumptions to make because it's coming out naturally from cooling of baryons. So it's not so exciting in terms of physics because it's not a revolution, but it's, yeah. And the statistics, above redshift 10, we have about 10-ish galaxies. Above redshift 7, we may have 25. So it's not huge, but it starts to be not small.
There was a question in Zoom by Dimitri Senikos. I think in a paper by Silicon Lobikov in 1993, it was saying that one can expect primordial black holes of multi-solar mass. Does it help to explain the?
Yeah, of course. There is a Silicon Rees paper as well, which was an old paper that was making seed black holes of 10 to the 5, 10 to 6 solar masses. And yes, of course it helps. Yes.
Other questions? Other questions on Zoom? Okay, I think if not, we can thank the speaker.
Thank you.
And keep talking and discussing the response. Thanks, everyone.
Jusqu'à quelles aides à peu près? En théorie, en observationnel.
Avec James Webb, jusqu'à quelle redshift on peut voir?
Ouais.